Hi there, 8th graders. This is going to be a quick review of Big Idea C when it comes to Don't Eat Yellow Snow. So I'm just pulling up the PowerPoints that we used before, and we'll go through those again in rapid succession here, and hopefully this is a system that works for you. So we've got our first set of notes here, C1. It's all about groundwater. Behold, my own notes, truly a thing of beauty. But what is groundwater? Well, the name kind of says it all. It's water that's soaked into the ground and is now stored underground. How does it form? Well, you guys know the water cycle now, so it forms mostly from precipitation, landing on the ground, and then soaking down through into the ground. So some of the vocab words like permeable. Permeable is any material through which water can pass easily. So sand is permeable, dirt is permeable. You get the picture. Now, this is my own wonderful example of what permeable might look like, permeable material. When you look at sand grains or dirt particles up close under a microscope, you would see that there are pore spaces, openings here between the particles because they don't fit together perfectly. And those are the pore spaces that allow water to move through. So what about impermeable? Well, impermeable is material through which water cannot pass easily. And so something like that might have the pore spaces filled with other material, so that there is no opening for water to move through. Clay is a really good example of that. Good solid igneous rock might be impermeable. All right, so zone of saturation. Well, if you look at my beautiful diagram here of groundwater, the zone of saturation is this area right down here. Of course, this grayish area at the bottom is the impermeable rock, and all of this through here is permeable. So as water percolates down through, it reaches the zone of saturation. It can't go down any further, so the water begins to just simply fill up the pore spaces. So this part of the ground right here is saturated with water, and that is the zone of saturation. It means that the pore spaces are filled 100% with water. Completely, utterly, totally filled with water. You can't get another drop into it. And that, of course, is the definition of saturation, like a sponge that's saturated with water. You touch it and water comes gushing out because there's no other places for it to go. So then up above, you have the same exact material, but the water hasn't completely filled in all of the pore spaces, and that would be the zone of aeration. And here comes the nifty little definition right here. It's the area where the pore spaces are not completely filled in with water. There's still room for other things like air, which is kind of, I guess, how in my own mind I keep the zone of aeration straight. So the water table is simply the boundary between these two zones, the zone of saturation and the zone of aeration. A good heavy rain will bring more water down through the permeable layers, and the zone of saturation will increase, and the zone of aeration will decrease. And if the opposite happened, if there was a long drought and there wasn't a whole lot of water coming down through the ground, well, then the zone of saturation would actually shrink and get smaller. The pore spaces would lose their water as it's sucked out of the ground, usually by us human beings. So there you are, boundary between the two zones. It's always in motion. The water table, it's up when there's lots of water, and the water table is down when we're in a drought. And that's pretty much it. So that's C1. So then let's take a look at C2, and I believe C3 are both together in here. So here you see a handsomely, devilishly good-looking person dancing around. No, that's not me. I believe it might be my twin brother, the good one. I'm the evil one, of course. So here's the question. What's water like as a molecule? What's it made up of? How does it act around other molecules? So no shock to anybody. The chemical formula for water is H2O. That's 2 hydrogen and 1 oxygen, something you probably all learned in elementary school. But you might not have been aware of what it physically looks like. This is how it's put together. The oxygen is here. The 2 hydrogen are slightly up above it, or I suppose down below it, depending on which direction you're looking at. I always liken it to something like Mickey Mouse ears, and you can see the Mickey Mouse ears right here. Here's a third image trying to show it with the actual electrons too. And what it means is the electron clouds are actually overlapping between these atoms, the hydrogen and the oxygen. What it really means is they're actually sharing the electrons. But that's what water looks like. And as it turns out, water then, therefore, is polar too. It has a positive end, which is over by the hydrogens, and it has a negative end, which is on the opposite side of the hydrogens. And because it's polar, that means that just like any other magnetic type of a object, it pulls on things that are polar too. Water is stuck on itself, you might say, because it's attracted to other water molecules. The positive end of one water molecule is attracted to the negative end of another water molecule. They like to hang around with each other. Kind of like science nerds. We all like hanging around with each other. And water is also attracted to anything else that's polar. And there are a lot of materials out there that are polar. I'm just going to breeze past this. This mostly was just helpful information for our salt lab, which we were doing at the time that we did these notes. So I'm just going to bump past that, and we'll wrap things up here and talk about C3 as well. But it turns out that like dissolves like. Polar molecules dissolve other polar molecules. They pull on each other. And dissolving is actually one molecule pulling another molecule apart, at least temporarily. However, now, polar cannot dissolve nonpolar. If you're nonpolar, you don't have anything to pull on. There's no magnetic pull. It's like being shocked and surprised that you had a giant magnet and it didn't do anything with that piece of wood that the person was holding. You know, they just don't interact with each other. Because of that, then, oil, for example, is nonpolar. Because oil and water don't interact with each other. The water doesn't pull the oil apart and dissolve it, so it's nonpolar. Sugar, on the other hand, is polar. Because the sugar and the water interact, the water pulls the sugar apart and dissolves it into it. And then, of course, sand, nonpolar, because sand doesn't really dissolve in water. And then moving on, talking about question C3, why is water known as the universal solvent? Well, it's because it's really good at dissolving things. And that's good news because it's what keeps us alive. Water can easily dissolve almost anything, including all the stuff that we use in our bodies to stay alive. The bad news is it can do the exact same thing to anything that's dangerous, like pollution. And so water is very susceptible to being polluted. So just to wrap things up here for C3, a couple quick vocab words. You have solvent, and that's any substance that does the dissolving. You have the solute, which is any substance that gets dissolved. And then the solution is just the mixture of those two substances, where one mixture dissolves, or one substance dissolves into another in a mixture. And there you have it right there. That's C2 and C3. And then to wrap up with C4, and we'll speak very briefly to C5. This is really quick and easy. After our Rogersville simulation and the work that you guys did making your posters, trying to warn people, public service posters, and the skits that you created, most people now are pretty aware of some of the more common sources of pollution. When it comes to groundwater, anything that we store underground is a potential for contaminant. So septic tanks, if they're not properly maintained, can leak into the groundwater and make people sick. As you can see on the picture on the right over here. Landfills, again, if they're not properly maintained, if they don't have a nice clay impermeable layer underneath them, they can actually bring bacteria down into our groundwater or other nasty chemicals too. Gas stations, same thing. Nuclear waste, if we were to be stupid enough to bury that stuff underground, that would not be cool. And large, and what I really should say here are industrial farms, not family farms. Family farms are not big enough to have a widespread impact, but you get into these large industrial, corporate-owned farms, and they are large enough. With that many animals, they can actually impact the groundwater underneath them. So there are all those pieces there. But the interesting thing is, these are all dangerous if we don't take good care of them. If we can properly maintain them, then we can avoid these problems. And of course, that was our big idea for Big Idea C. I'm going to skip past that simulation and take you right over here to surface water. And remember that surface water would be anything that's on the surface, lakes, streams, rivers, marshes, all that kind of stuff. And so things that are on the surface can impact surface water. Urban runoff's a big one. Gasoline, oil, salt, all that stuff that gets off of our cars or falls from our cars onto parking lots, onto pavement, eventually can wash into the ground. And if you've ever been on after a heavy rain or on a wet, soggy day, you've been out in the parking lot, you can see the water and it's got kind of a colorful rainbow film to it. Unfortunately, that is oil and gasoline that's in the water. Fertilizers and pesticides can be a problem if they're over-applied, used too frequently, and they don't soak up into the plants or are used by the plants, they end up down into the water. And you can ask the good folks living up by, gosh, I'm blanking on the lake name here. You guys have to fill it in for me. The lake up by Rice. But they have the summer blooms, the algae blooms every summer. And so that's a problem. Thermal pollution, that's just when like a factory or a company would discharge warm water into a river or a lake that's really cold. And there's no chemicals in it, but the warm water can be dangerous to fish. It can shock them and kill them. Water traffic, boats, things like that. And of course, factories, if they're using water, as you can see in this picture right here, or discharging waste out into the water, that can be a problem. And then our final question, C5, was really about whether or not bottled water is better or worse, or not any different. And we did our experiment here in class earlier in the week, and we found out that, yeah, bottled water is not any better number-wise with all those different tests we did, the chlorine, the iron, the nitrates, nitrites, copper. It tested out just exactly the same. In fact, it's slightly more dangerous because these bottled water sources do not have small amounts of chlorine in them, which city municipal sources do put in to help kill off the bacteria. So they're actually a little more dangerous bacteria-wise. But taste-wise, no difference. Safety, no difference at all. So, you know, and we talked about this in class, the dangers of all these bottles. Only about a quarter of bottles, actually plastic bottles, get recycled every year. A lot of them end up in landfills, and worse yet, some of them end up in the ocean. The Pacific Ocean garbage patch, for example, is one such case, which is kind of sad. You got all this plastic out there and it doesn't decompose. It just sits out there. And then in class, we also talked about ethically bottled water and the fact that there are a lot of people all around the planet that don't even have access to clean tap water. And maybe we should be spending our resources instead of on bottled water, trying to help provide clean tap water for other folks so that we can bring down infant mortality rates. I believe the statistic from the World Health Organization was 1.4 million children die every year from dirty water, from contaminated water. So maybe this $4 billion a year industry, maybe we could spend that $4 billion elsewhere if we choose to. So there you have it in a nutshell. There's C4, and of course the big idea, now that you've waited a whole 12.5 minutes for it, the big idea is that a smart person or a clever person can solve a problem, but a wise person can avoid it. And hopefully you avoid the problem of not doing well on your Common Craft video or not doing well on your upcoming test, and you're able to study and pull all this information together in your ISN. Wish you all the best and looking forward to your final projects, whatever they happen to be. So peace out.